Hi, everyone. So I would like to talk about the Cauchy-Riemann equations today, which are one of the central tools that we use in complex analysis that we don't, at least ostensibly, don't have access to in real calculus. So you can think about the Cauchy-Riemann equations as a tool that can use to check to see whether or not a function is analytic. It's nice to have a certificate for the analyticity of a function when it's not obvious what the power series of the function might be. Obviously, if we have a power series with a non-trivial radius of convergence, the function is going to be analytic. But in the case that we're faced with a function where we don't necessarily know what the power series is, especially at this point in the class, because we don't have access to Taylor's theorem yet, a certificate for analyticity is very important to have. So you can think about the Cauchy-Riemann equations as sort of being related to Clairaut's theorem from two-variable calculus. And what Clairaut's theorem tells you is that mixed partial derivatives must be equal to each other for any function that has continuous second derivatives. And the same sort of rigidity of that kind of function is going to apply here. These are also related to conservative vector fields in the study of multivariable calculus. So let's actually state what the theorem says, and then we'll do some examples of testing to see if functions are differentiable, or sorry, to see if functions are analytic. So this is what the Cauchy-Riemann equations actually say. So this is where most people remember, is that if you begin with functions that are real valued, so these are real valued functions, u and v. So we're starting with two real valued functions, u of x and y, and v of x and y, and these are real valued. Then we test this system of equations involving partial derivatives. So we'll come back to what the conditions are in just a second, but the idea is that I have this system of equations that looks like the following. The partial of u with respect to x, xy, is equal to the partial of v with respect to y of xy, and the partial of u with respect to y of xy is equal to minus the partial of v with respect to x of x and y. So this system of equations together is called the Cauchy-Riemann equations, CRE. And functions that satisfy this system of equations are very special. That is to say that if I have a function that I can build out of the pieces that satisfy this, so if I take a function f of z, and I turn the u into the real part of that function, and I turn the v into the imaginary part of that function, so this thing now is a complex function. I've used u as the real part, and I've used v as the imaginary part. Then that function is differentiable if and only if the pieces satisfy the Cauchy-Riemann equations. So f is differentiable on a disk if and only if u and v satisfy the Cauchy-Riemann equations. That means that we have a certificate for telling when a function happens to be analytic. Because remember, one of the big theorems here is that differentiable once implies differentiable forever. Okay, so this is sort of the when I say certificate, what I mean is it's a test, right? So passing the Cauchy-Riemann equations tells you that you're looking at pieces of an analytic function. Okay, now the proof of the Cauchy-Riemann equations is an interesting proof, I think, because it involves basically application of very straightforward two-variable calculus, but then some estimates from analysis that are sort of interesting. So I'm going to put the proof of the Cauchy-Riemann equations in a separate video. And for this one, what I want to focus on is sort of how we can use it and what the applications happen to be. So we should check and make sure that we understand what the rest of the hypotheses say here. So let's take a look more closely at the hypotheses. So we have pieces u of x and y and v of x and y that are real valued, and they have to be C1. So to be a C1 function is to say that you have continuous first partial derivatives. And it's not enough that they're continuous at, like first partial derivatives at a point. Just like the rest of what we do with complex analysis, we're insisting that we have differentiability on a disk. So there's some open set on which these functions are nicely behaved, because it means that the graphs of the functions are smooth in some sense there. There's no kinks or corners that can screw this up. So the picture that we should have is that we're always working on some coordinate axis. So I can think about this as being the real part of z, and this is the imaginary part of z. And I have some point A, which I can think of as a complex number. It is surrounded by a disk. So this S is equal to a disk centered at A and with positive radius. And what we're insisting on is that here, actually, I guess technically, I suppose we're imagining that we're in R2 here, right? Because these are real valued functions. And so I guess the idea is that we're thinking about z and x and y as sort of interchangeable with each other, right? So z is equal to x plus iy. So I'm thinking of the complex plane and R2 as sort of identified in that sense. Okay, so this circle that I'm drawing here, I can think of as being a disk in R2 for the x and y inputs, or I can think about it as a z value, and I'm just coming around the disk with all the complex values that are in that same disk. This is an identification, so I can think about it either way. So the idea is that if I think about the complex number z is equal to x plus iy in this disk, and I have u of x and y real valued, and v of x and y real valued, then what I insist on is that ux, uy, vx, and vy are all continuous. So that's what I mean by continuously differentiable, is that I have derivatives everywhere, and those derivatives are continuous everywhere they're defined. So these are also called C1 functions, or functions of class C1. It's one of the mildest conditions you can put on functions that are actually useful. And with that setup, then we can test these pieces to see if they happen to be pieces that represent some analytic function. And in the other direction, what that tells us, if we have a function that we can sort into a real part and an imaginary part, I can use those pieces as u and v that I can test with the Cauchy-Riemann equations to see that this function is actually analytic or not. So here's formally our definition. The Cauchy-Riemann equations is the system of differential equations given by ux is equal to vy, and uy is equal to minus vx. The reason that that negative sign sneaks in will be apparent once I compute the, if you're interested in where that comes in, you can look at it in the video on the proof. It actually comes from taking the complex derivative, and the I being involved like sort of sneaks in and turns one of the equations into the negative of the other one. So more importantly, we should look at how we apply these things. So I'm going to start with a function that I know is analytic because it has a power series, because it's a polynomial. So f of z is equal to z squared. Suppose we actually wanted to see that that function was analytic using the Cauchy-Riemann equations. Well, we should write it down in terms of its real and imaginary parts and define that to be u and v, and then test them by putting them in. So if f of z is equal to z squared, then that means that it's equal to x plus iy squared. Remember, I need to sort this into a real function of x and y and an imaginary function, or the imaginary part, which is v of x and y. I can, multiply this out, and I'm going to get x squared minus y squared plus I times 2xy. That's the result of foiling everything out, sorting the terms into real and imaginary parts. So let's let the function u of x and y be equal to x squared minus y squared. That's the real part of f. And we'll let v of x and y be equal to 2xy which is the imaginary part of f. And I'm going to remind you that real and imaginary parts of complex numbers or complex functions are real valued. The I is what turns it into sort of a complex object. So let's test and see if these satisfy the Cauchy-Riemann equations. So the first of the Cauchy-Riemann equations says that ux must be equal to vy. Well, ux is equal to 2x, and vy is equal to 2y, and those are equal. So we satisfy ux is equal to vy. First of the Cauchy-Riemann equations satisfied, unsurprisingly, perhaps. On the other hand, we can look at uy. So the partial derivative with respect to y of u is minus 2y, and vx is equal to 2y, which are the same but negative. And so it is the case that uy is equal to minus vx, and that is also satisfied. Since both equations are satisfied, we know that this function is once differentiable, and once differentiable in the land of complex analysis means once differentiable on an open set means infinitely differentiable in an open set. The one thing we should check that I didn't, and you should pay attention to this, is when we take the derivatives, we should actually make sure that the functions that we get are continuous functions. So when I look at this, I say, okay, are all of these pieces that came out, are these continuous? Does this have continuous derivatives? And the answer is yes. This is a hypothesis that's very important when we're testing this, is that the derivatives themselves are also continuous. So yes. So the combination of the derivatives being continuous and the Cauchy-Riemann equations being satisfied means that we can conclude that f of z is equal to z squared is an analytic function. Now, more interestingly, often what we do with the Cauchy-Riemann equations is we can test to see that certain functions fail to be analytic. And in particular, you might wonder, well, we have everything, when we're talking about analytic functions, we're always talking about z, but we never talk about the complex conjugate of z. What role does that play in all of this? And part of the reason why we haven't seen very much of it is that it turns out that the function f of z is equal to z bar is analytic nowhere. So complex conjugation is not compatible with analyticity, and we can test that directly using the Cauchy-Riemann equations. So as before, we will define the function, we'll figure out we'll chop f into its real and imaginary parts, and we'll test those pieces using the Cauchy-Riemann equations. So if f of z is equal to z bar, that's equal to x plus iy bar, which is x minus iy. Well, that's pretty easy to tell what the real and imaginary parts are, which is where we're going to get our definitions of u and v. For this function, u, which is the real part of f, is the function x, and v, which is the imaginary part of f, is the function minus y. And now let's just check using the Cauchy-Riemann equations what's going on here. Well, ux is 1, and uy is 0, and vx is, maybe we should go the other way so we get a direct comparison here. Vy is minus 1, and vx is 0. Now, one of the Cauchy-Riemann equations is satisfied. It is certainly the case that uy is equal to minus vx, trivially, because they're both 0. On the other hand, ux is not equal to vy. So that means that we fail to satisfy the Cauchy-Riemann equations. And not only that, we fail to satisfy the Cauchy-Riemann equations at any point. They always fail to be met. And the conclusion is, since the Cauchy-Riemann equations are not satisfied, it must be the case that f of z is equal to z bar is analytic on no disk. So there's nowhere where this thing is going to have a power series that converges absolutely. Okay, so that's a basic application of the Cauchy-Riemann equations. We'll be using them as a different tool later on when we know a little bit more about the development of Taylor series and for particular functions. But this is the big test that we use when we encounter some unknown function where we don't necessarily have a power series, or we have not derived a power series, as a certificate for showing if a function is analytic or fails to be analytic. or if a function is analytic at a particular point or fails to be analytic at a particular point. There are functions that are not analytic everywhere, and we can test those things with the Cauchy-Riemann equations as well. All right, so this is one where some exercises I think will nail down sort of how we use the Cauchy-Riemann equations and the sort of way that functions can be ripped apart into pieces. It's not always as straightforward as it seems, because it's not always easy to directly compute the real and imaginary part of functions, but it's still one of the sort of crucial foundational tools for investigating what's going on. Now, I will also put in the post for this one, there's a really interesting, a couple actually on YouTube, interesting videos exploring the connection between the Cauchy-Riemann equations and the underlying notion of conservative vector fields from multivariable calculus. And it turns out these things are intimately connected to each other. And it's not a connection that's always drawn out in the context of complex analysis, but it is the sort of connection that gives you a strong, there's just a strong relationship between the very rigid geometry of vector fields in R2 that happen to be conservative, which are the natural vector fields of physics in a lot of ways, and analytic functions. And so in a really deep way, analytic functions are natural objects. We haven't just thrown away interesting stuff to get analytic functions. Analytic functions, in some sense, correspond to one of the basic objects of physics. So they are natural objects to use. All right, so I will post that, and then I'm looking forward to your feedback on my test video on the chalkboard. I could have done this way too, but I'd like to hear from you first. All right, I'll talk to you guys soon.